Have you ever stopped to think about how we actually see? I mean, really think about it. It all starts with a single ray of light, but it ends with this incredible, vibrant world inside our heads. So let's break it down.
To understand sight, we have to start in the dark. Without any light, there's no information. There is just nothing.
But the second you introduce light, boom, the potential for vision just floods in. So how do we make that leap? How does a simple beam of light transform into the rich, colorful world you and I experience every day? That's the big question.
All right, so what's the very first step in this whole process? Well, for you to see anything at all, that thing has to interact with light. It's really that simple. Basically, everything you see falls into one of two categories. On one hand, you've got your luminous objects, things like the sun or a light bulb. They're the superstars, making their own light. And then there's everything else, the non-luminous stuff, like a chair, a book, even the moon. They don't create light, they just reflect it.
And right there, that's the absolute key. The vast majority of what we see isn't making light at all. We see it because light travels from a source, hits that object, and then bounces directly into our eyes. That bounce is everything.
Okay, so if seeing is all about this bounce, then how exactly does that work? What are the rules of the game? For that, we've got to look at the physics of reflection.
So reflection, in simple terms, is just light hitting something and bouncing off. It sounds pretty basic, right? But this simple act follows some incredibly strict and predictable rules.
And here they are, the two unbreakable laws of reflection. First, the angle that light comes in at is always the exact same angle it goes out at. Think of it like a perfect bank shot in billiards. And second, the incoming ray of light, the outgoing ray, and an imaginary line sticking straight out from the surface, they all exist on the same flat, two-dimensional plane. Every single time. No exceptions.
So wait a minute. If light is bouncing off of literally everything according to these rules, why can I see my face in a mirror but not in, say, this wooden desk? It's a great question.
And here's the answer. It all comes down to the texture of the surface. On a super smooth surface like a mirror, all the parallel light rays hitting it bounce off in the same neat direction. That's regular reflection, and it gives you a crisp, clear image. But on a rough surface, even one that feels smooth to us, those light rays hit all the tiny bumps and scatter in a million different directions. That's called diffused reflection. It lets us see the object's color and shape, but it completely scrambles the image.
Okay, so let's stick with that perfect, regular reflection for a bit. Let's talk about mirrors and some of the really cool, almost magical things that happen when we use them.
The image you see in a regular flat mirror always has a few key things going on. It's upright, not upside down. It's the same size as the real you. It looks like it's just as far behind the mirror as you are in front of it. And of course, there's that classic left-right switcheroo.
That left-right reversal, which has the fancy name lateral inversion, is actually used in a really clever way in the real world. The word ambulance is printed backward on the front of the vehicle, so when you look in your rearview mirror, the reflection flips it back the right way so you can read it instantly. Pretty smart, huh?
Now, things get really interesting when you add a second mirror into the mix. You've totally seen this. You're at the hairdresser, and they hold up a second mirror so you can see the back of your head. What's happening? Light is bouncing from your head to the big mirror, to the small mirror, and then finally into your eyes. That's multiple reflections at work. And we can actually predict how many images you'll see. For instance, if you put two mirrors together at a perfect 90-degree angle, you don't see two reflections of yourself, you'll see three.
And here's where it gets a little bit mind-bending. The smaller you make that angle between the mirrors, the more images you get. And if you make the mirrors perfectly parallel to each other, well, the light just bounces back and forth forever, creating this incredible tunnel of infinite images.
So, we've talked about how light bounces off things, but light does more than just reflect. What happens when it actually passes through something, like a prism or even a drop of water? Well, that's where all the color comes from.
The scientific term for this is dispersion. It's the process of splitting what looks like plain white light into all the colors hidden inside it. And the most beautiful, most famous example of this is, of course, a rainbow. That's just sunlight being split apart by millions of tiny water droplets hanging in the air.
And those colors that make up white light are always the same, and they're always in the same order. Violet, indigo, blue, green, yellow, orange, and red. You probably learned the acronym in school, VIBGYOR.
That right there is the visible spectrum of light.
So, we've got light bouncing off stuff and we've got light splitting into colors, but none of that means anything without the final piece of the puzzle, the incredible biological camera that actually captures all this information, the human eye.
The journey of light inside your eye is just an amazing piece of engineering. First, light comes in through the cornea and the pupil. The colored part, the iris, opens and closes to control just how much light gets in. Next, the lens inside your eye focuses all that light, projecting a sharp image onto the retina at the very back. Now, the retina is lined with millions of special cells, rods and cones, that turn that light into electrical signals. And finally, the optic nerve zaps those signals straight to your brain for processing.
But here's the final, incredible twist in the story. Because of the way the lens works, the image it projects onto your retina is actually upside down. So if the picture our eyes are actually seeing is inverted, how is it that we perceive the world as right side up? Well, the answer isn't in the eye at all. It's in the most powerful computer on the planet, your brain.